Hi everyone, Shirreff here from Mount St. Vincent University, professor of chemistry and physics and the host of this program, Conversation with a Scientist. And today is my great pleasure to talk to Professor Marianne White, the Harry Shirreff Professor Emerita of Chemical Research at Dalhousie University here in Halifax as well. Professor White obtained her Bachelor of Science in Chemistry from the University of Western Ontario and her PhD from McMaster University, which was followed by an NSERC postdoctoral fellowship at the University of Oxford. For those who are not Canadian, the NSERC is an abbreviation that stands for the Natural Sciences and Engineering Research Council of Canada. And Dr. White is a world-renowned scientist in the field of material sciences. Material science, I think, is singular. Materials science, yes. Right? Yeah, sorry. So she has a long list of accomplishments. We're going to go through some of them today. Of course, not all of them, otherwise we're going to spend the whole day. And original contributions to science, science education, science outreach, and science policy. So Dr. White has published more than 200 refereed scientific papers and a very well-known and widely used textbook that is used by universities worldwide in courses on material science. Here it is. We're going to get to this book more later on in the program. This book is now in its third edition. It's quite extensive, and we're going to talk about it a little more. Dr. White has led research projects that received government and industry funding that exceeds $17 million over her career. And she has served in leading roles in panels, societies, and research funding organizations in Canada and internationally, including, just to name a few, the NSERC that we just defined, the Canadian Society for Chemistry, the Canada Foundations for Innovation, the International Union of Pure and Applied Chemistry, which is abbreviated, the famous abbreviation as IUPAC, for those chemists that would recognize this abbreviation right away, and for the International Council on Materials Education. For her work, Professor White received numerous awards, among which we mentioned just a few here: the McNeill Medal of the Royal Society of Canada, the American Chemical Society Award for Incorporation of Sustainability into Chemical Education. She was elected as Fellow of the Royal Society of Canada. She received 3 honorary degrees, 3 doctorates of science degrees, honoris causa, from the universities of Ottawa, Western Ontario, and McMaster. And most importantly, the jewel in the crown, so to speak, is her election or appointment in 2016 as an officer of the Order of Canada, which is, for those non-Canadians, is the highest civilian distinction in Canada. And we will come back to this point later on. Marianne White is one of your main sustained interest in bringing science to the general public. Hence, this program is right on the spot.
Absolutely.
Right. Welcome to the program.
Thank you so much.
Thank you for being here.
Thank you for inviting me, Shirreff.
So it is a tradition of our program to delve a little bit into the personal aspects of the scientists and to show that the scientists are really human beings like everybody else, and they have other interests and other aspects of their life. They are complex beings as everybody else, and hence you've been very kind and brought some images from your early life and career to show the audience, which we will go through now. So now we can turn on to the pictures. So age 4. So take it from here, Anne. Marianne.
Well, that's me just before I started school at age 4, and cut off from the picture are my 2 brothers who were ages 5 and 6, I guess. And that was my early life growing up in London, Ontario.
Okay. age 17.
Well, this is just before I started university. This was about 2 weeks before I started university.
Any interest in science at this point?
Absolutely.
Oh, okay.
Yes, all through school. In fact, I went to a high school reunion once some years ago, and I hadn't seen people because I moved away from home a long time ago. I hadn't seen many people for a long time, and they all guessed I was a scientist.
And chemistry in particular, or physics? Or
Chemistry and math were really my strong points in high school. And physics, I'm sorry to say, my physics teacher told me that I would never make it in physics, but I could tell you I've been also professor of physics. So
well,
there you go.
Your current field is like...
Right on the line between chemistry
right.
and physics.
It includes a lot of physics, right?
Yeah. He told me girls couldn't do physics. Turned out
we're going to get to that
so
again.
much the case.
Yeah, we're glad that the times have changed and, the culture has evolved from these prehistoric times when people were thinking that women cannot do STEM for some unknown, strange reason, right? Yeah. So age 17,
Yes, so I think I was 21 here. This was my first lecture ever. It was my presentation of my honors project at an undergraduate chemistry conference. Southern Ontario Undergraduate Chemistry Conference. And I'm so glad somebody actually took a picture of that.
And it was a chalk talk?
Yes. No, I had slides, but
Slides.
this was during the question and answer period, I believe.
Yeah.
When the lights were back up. So.
Okay, all right. And this one?
This is the day I graduated from Western with my BSc. And that was just coming from graduation or going to, I'm not sure which. My father took that photo. And I added to this slide the slogan, "Why not?" 1975 was designated by the United Nations as the International Women's Year. And there was a lot of talk about women should be playing a full role in society. And the slogan was, "Why not?" And here I was finishing my BSc and about to start directly into a PhD program in chemistry. And I would say timing is everything in life. And even a year before, people would have really looked askance at me doing a PhD in chemistry. But in 1975, I had an international answer. Why not? Why not, indeed.
Wow. Very interesting. And this one?
This slide is a picture of me presenting a poster on my PhD thesis. Just before I was writing my thesis and over the months after this conference, I was definitely head by head down completing my PhD thesis. This conference was at University of British Columbia, and it was the first time the Canadian Society for Chemistry conference had posters. And I won a prize.
Wow, congratulations, belated. And do you remember what was the topic of your presentation here? And you're pointing at one particular slide which says heat capacity of, I can't read the formula.
CHD3. This was partially deuterated methane. And that was what my PhD thesis was on very low temperature, millikelvin temperature properties of solid methane. A rather esoteric topic, but it prepared me for my life's work.
Oh, great. So now we move to the multidisciplinary program at Dalhousie University. And here you are... Can you comment on this picture, please?
Yes. Yeah. This was the beginning of the Institute for Research and Materials at Dalhousie, a multidisciplinary research community that we built. There were 4 of us who were founding members, and I was the founding director and served for 2 terms as director of IRM, bringing together people from lots of different areas working to solve major materials research problems.
And this institute is still around, right?
It is, but it's changed its name. It's now CTRI, Clean Technology Research Institute,
right.
with more of an emphasis on clean technologies.
And that was your idea?
The IRM was my idea along with other like-minded people, yes.
Okay. How about this?
This was a program that I also was director for. This was an NSERC Create program, which was a collaborative research and training program called DREAMS, Dalhousie Research in Energy, Advanced Materials, and Sustainability. And it was a training program for undergraduate students, graduate students, and postdocs to learn how to think really collaboratively with other disciplines and also to spend some time in industry or other research labs outside of Dalhousie University as part of their training. And this was a tremendous program. I really enjoyed working with these students and the other researchers and seeing everybody reach so far and introducing sustainability, especially into our program in a very concrete way with workshops that we held with international level participants in these programs. And I really thought this was kind of the pinnacle of my educational aspects.
And the abbreviation is right on the spot.
Yes.
I love the abbreviation.
Thank you.
Dreams.
Yes.
Yeah. So honors, let's talk about your honors here, honorary degrees. For non-academic viewers, Marianne, can you explain the difference between an honorary doctorate and a regular doctorate?
Regular doctorate is an earned degree, earned by doing research and then writing a thesis. And that would be a PhD or a doctorate degree, Doctor of Philosophy degree. And that takes a long time, probably minimum 3 years, could be as much as 8 or maybe even 10 years in some cases, because you have a project and you're trying to crack this nut and figure out what's going on. So it's a bit open-ended. Honorary degree is the most amazing thing because you don't have to do anything to earn it except have a career. And somebody contacts you.
Well, you've done the career.
Well, okay. Someone contacts you and really makes more than just your day by saying, we'd like to present you with an honorary doctorate. So it's purely honorary. Sometimes they're given to alumni of the university to also reflect honor on the university. Sometimes they're people with no connection to the university, but they would like to highlight them. And very often, the only obligation is to give a convocation address, which is kind of the last words the graduates hear. And that in itself is an honor.
But it's a very high honor, and it's a very rare, award.
Absolutely.
Not a lot of people get honorary degrees.
No, absolutely.
Yeah. And the jewel on the crown here, the Order of Canada. So
this, again, was something that you can't push for, and it was totally unexpected, like the honorary degrees. I just had a call from the Governor General's office on my answering machine when I got into work one morning, saying to call them. I had to go and give an hour-and-a-half lecture before their offices opened. I called them wondering, was I in some sort of trouble? They can't take away my citizenship because I was born here. But anyhow, they asked me if I would accept a position in the Order of Canada, and I was totally blown away. Yeah, absolutely. Really thrilled. And then I had to keep it quiet for several months, which was
a
little hard until they do the official announcement.
Well, that's torture to keep it for several months.
Yes.
Right. And the little pin that you have, that's the Order of Canada for those non-Canadian audience. This pin is the smaller version of the medal and the
as
collar.
Per your request, I did bring
thank you so
my
much.
actual medal.
Oh, thank you for bringing it, Marianne. It's really kind of you to do that. And when do you wear the actual collar rather than the smaller version?
Okay, the smaller version is for everyday use. I don't wear it every day, like not when I'm just home washing dishes. But I do try to wear it when I go out because David Johnston said to us, wear that with pride. And when people ask you what it is, tell them. And I really took that to heart. But the larger medal I wear when I preside at citizenship ceremonies. Members of the Order of Canada are privileged to be invited sometimes to preside at citizenship ceremonies.
For new Canadian
citizens. Yes, and to do the actual oath for
in the court.
Actually, they could be anywhere. They could be in the citizenship offices or we wherever they decide to hold them. I've done one at the Halifax airport. I've done them at Pier 21. That was my most recent one. Other places, public venues, sometimes they're open to the public. And to be able to give the Welcome to Canada, Canadian citizenship speech to the new citizens and to actually do the oath, present the oath with them is really, really a privilege.
Wow. And what does it represent, actually, the snowflake?
Well, the snowflake is meant to represent the snow view of Canada. And it's based on a real snowflake that was sketched first or photographed by a Japanese snowflake researcher, snow crystal researcher in Hokkaido, Japan.
Oh, okay.
And it's a very simple, probably the simplest one to make. And the science behind this shape of the snowflake is also something I'm pretty interested in.
Because of material science.
Yes.
So, yeah.
So it's extra special for me.
And they say in Latin, it's the desirantes meliorium patriam.
Yes.
Which means?
They desire a better country. Yes.
Those who are appointed to the order.
Yes.
Yeah. Has it influenced you after the award in any shape or form?
Oh, I think there are times when I have to and maybe everybody should do this anyhow, just watch my mouth or my pen when I'm saying something, because there's a little extra weight when you have those initials OC after your name. So there's a level of responsibility. It's privilege and responsibility always go hand in hand. And I've been very privileged, and I try to be also very responsible.
Well deserved, Marianne.
Thank you.
So let's turn now to your research that brought all these recognition, in fact. What is materials science in simple words?
Well, in a diagram, which is how I always like to think, we would say that materials research and materials science is the relationships between and among structure, properties, performance, and processing. And we like to draw that on a tetrahedron, because you would recognize that all of those interactions are equal in all directions on by placing those on a tetrahedron. And chemists would think about the structure of the material, physicists maybe a little bit more about the properties of the material, and engineers more about the processing and the performance. But you need all of those to make a material work.
And your lab's focus was on phase change materials, right? And thermoelectrics and thermochromics.
Yes.
All central to sustainable technologies, as I understand it.
Yes, that's correct.
So what do these terms mean?
Okay, those are all really about the properties. So this is where my work just walks the line between chemistry and physics, looking at different structures and how they have different properties. But they're all about how these properties change with temperature. So if we take, for example, thermochromic materials, these are materials that change color with temperature. And I first got interested in these because of something that was kind of a gimmick that was around in the 1990s. It was T-shirts that changed color with temperature. A not well thought out idea, because a lot of people, the color change was mostly under their arms. So not very appropriate, but they were pretty popular for about a year. And of course,
it draws the attention at places where they may not like to have the attention.
Right. But people started asking me things like, well, this changes color with temperature. How do those work? And I started to look into it, and I realized that there were different ways that materials can change color with temperature. But for a large category of them, the science was not well understood. And we spent quite a bit of time, several PhD students, working on trying to understand thermochromic materials and how they work. So the materials I'm talking about are called three-component. In other words, they have three parts to them. There's something that's called a dye, something else called a developer, and something else called a solvent. And the solvent can melt, and that's what triggers the change in the color. And the dye has two different states. One of these states, it's colored, and the other state, it's not colored. So it's called a leuco dye. Leuco means white. So it's white, but it can become colored. And it can become colored if the developer can interact with it. So if this is melted, the whole mess of three things is melted and quickly cooled into a metastable quenched solid, it's colored. And that's what I'm showing in the top left-hand diagram. The dye is colored and the whole material is colored.
And it's blue in this case.
Yeah, this is blue in this case. And actually blue is quite a common one. But if you let this sit for a while, that's colored because the developer is interacting with the dye. I've shown the developer cartoon molecules pointing towards the dye. And that makes the dye...
Little triangles.
Little triangles,
great
yes.
triangle.
Are pointing towards the dye, and they're interacting with the dye in a chemical interaction. But after they sit for a while, the developer would really prefer to be with the solvent. And after they sit for a while, as shown on the right-hand side, the developer is now forming a compound, 2-to-1 compound in this case, with the solvent, and it removes it from the dye, and therefore the color disappears. Now, the really interesting thing about this type of thermochromic system is you could have colored or uncolored depending on the thermal history, whether it's history, whether it's just been cooled from the melt and you get the blue, or you let it sit for a while and you get the colorless. Or you can also introduce the
So it's
lack
not
of color.
reversible?
It is reversible, because then you could heat it up again and melt it and get it to reverse and go back to the blue and then bring it to the white. So you can play with that. And some people might have seen also commercial products that make use of this. This is a pen, and it's called Friction Pen. It's from the Pilot ink company in Japan. And this pen, this is actually a highlighter pen. You would use it to draw on a piece of paper. And then if you want to erase, this end, there's not an eraser, is actually a heater. You just rub it across the paper, it heats up the paper, and it takes it from the colored state to the uncolored state.
Which is a stable one, and hence it will remain.
That's right. And if you want to buy these, you could buy any number of colors at the fabric store, because quilters use these to draw their markings of where they're going to be sewing on their quilt. And then later, when they want to erase the color,
want to remove
they just iron it. And now the dye, all those components are still there, but you can erase the color with an iron.
How about secret ink that spies use?
Actually, one of my interactions in this work was with Toshiba in Japan, because they wanted to develop a type of toner that you could print it on paper, and then later when you wanted to use that paper again to conserve paper, you could heat up the paper, remove the coloration of the toner, and print on that paper again. And they developed a product based on the chemistry that we had derived and published on.
To conserve tree and hence sustainable, right?
Yes, yes.
I see.
Yep. And that was called E-Blue ink.
E-Blue.
Yes.
Yeah, so how about heat storage materials now?
Okay, well, we have been working on materials that will store a lot of energy in a very small amount of material. And any material, which we often call a sensible heat storage material, like a brick or thermal insulation, that will store some energy as we heat it up in temperature. But a phase change material changes phase. And in that phase change, often melting, it stores a lot of energy, thermal energy, in a very short transitive temperature. And we can use materials like this to store energy that otherwise would be wasted. About 70% of the energy that we use in society actually is dissipated as waste heat. So there's a tremendous low-hanging fruit there for us to capture, getting that waste heat and then being able to make use of it again.
And you can convert it to electricity, for example, or you can convert it to what?
We really want to convert it to heat, because heat to heat is a very efficient transformation. And about 30% of the world's energy is used to heat. So if we're wasting that energy, it's just dissipating, and we could capture it like a thermal battery and then use it again, then this is a tremendous advantage.
And this is your US patent
Yes, this is
2022?
Yes, one of the most pressing problems is that phase change materials, when they melt, they don't transfer heat very well. Their thermal conductivity is quite low, and they melt easily. But when you go to solidify them, they become like a thermal insulator on your pipes that you want the heat to be transferring.
Okay.
So we've developed a type of phase change materials that's a porous ceramic material which conducts heat really well, and we can put the phase change material in there, and it will melt, but it doesn't flow away. It stays in the pores. It's like a sponge.
Wow.
So we're overcoming the major problem of thermal conductivity.
Has
being
it
low.
been adapted in an industry?
Not yet, but we're really working with industry to try and have that happen.
What kind of industry would jump on this?
Type of industry that is interested in conserving energy. So building industry and anything where remote locations where you have to really be very conservatory of the energy that you use.
So materials research here, this is a summary, I guess, of the conceptual summary?
Well, this is really the challenges of materials research, that we still have structure, properties, processing, and performance. But actually, to make good use of materials entirely and to develop new materials, we have to think about a lot of different aspects. We have to think about how much energy does it cost to make those materials if you want them for energy conservation. We have to talk about the availability of the elements, because we can't make new elements. We have to conserve the elements that we have. We have to also think about the economics. No point in making something that's too expensive that nobody wants to use. And these days,
it's a lot of balls to juggle.
Yes,
right?
and some way beyond our control, like the politics of the situation. If you just think about rare earth materials, and how at one time in North America we mined a lot of rare earths, then they were being mined in other parts of the world, and the mining fell off in North America, and now those other parts of the world are not being so freely flowing things, and so the political side of things is also an aspect there.
This is very interesting. So I will get back to your book now, this book, this very well-known textbook that is used in universities worldwide, Physical Properties of Materials. So you wrote this book, and this is now it's in its third edition. So what inspired you to embark on this monumental effort, to write this? How many years it took you?
Okay, probably
monumental.
Forever. let's put it this way. My daughter, who probably doesn't want me saying her age now, but she told me she doesn't ever remember me not writing this book. So it's taken a long time. In the late 1980s, I heard a public lecture, chemistry professor who was visiting, and he said something like, you all know how a photocopier works. And I was thinking, okay, this room is filled with chemistry students, chemistry professors. How many people here actually would know how a photocopier works? And where would we ever teach that in our curriculum? Well, at that same point, we were going through a curriculum review for physical chemistry. And I proposed that instead of teaching more traditional physical chemistry, we teach it through aspects of materials research, still invoking those same physical principles and teaching that, but using the angle of materials and their role in our lives. So we would be producing...
To spark their interest,
yes,
the students.
And graduates who knew something about how the world works. So I started preparing a course like this. And in 1991, I went on a lecture tour for the Canadian Association of Physicists talking about physical properties of materials. It's a very fun tour because I had lots of lecture demos and people told me all their best demos when I visited different universities. I think I went to 12 universities over the course of 2 weeks. And many, many people said, oh, we'd like to give a course like that too, if only there was a book. So I came home and I thought, okay, I'll start writing my lecture notes into a book and we'll just see where it goes. So the first edition was published in 1999, and then another one in, I forgot what year, 2006, I think, and then another one in 2018.
I remember as a graduate student, I mentioned this to you, Marianne, that as a graduate student at McMaster University, one of the professors there adopted your book in one of the courses while I was a graduate student. So this is the first time I've encountered this important book, and it was the first edition indeed, because it was the late 90s, beginning of the late 90s,
yes,
1990s, yeah. And the third edition includes 300 plus problems, right, which is this edition that we have here, and tutorials and 500 entry, a glossary that has 500 entries. So what's the idea here?
I wanted to use this as a textbook, and I thought, well, I'm going to be teaching a course from this, and I should have problems for the students to work on. So I put in initially the problems I was using, and then I added more problems and more problems and more problems, and the more I would think of something would trigger, oh, that would be a good problem. So I just kept writing them down, and that's how so many ended up in there. And the glossary really came from being on supervisory committees of graduate students, that I often found that people were not using terminology in materials research in a good way, just not an accurate, clean way. And I had considered writing just a separate glossary of materials terms, but I thought, well, probably nobody's going to buy that.
So you included
so
it
I
here.
included it in the book, and it just makes your thinking a little sharper when you use the exact terminology. And they're just short definitions, but then references to areas in the book where you could look at a little bit more detail.
So what is your strategy in this book to make challenging, complicated concepts of material science into, intuitive for the reader,
Okay, well, I think the first point was how to present materials. And there are two ways to do that. And there are some other books that take the first approach, which is by category of materials. You could talk about metals, you could talk about insulators, you could talk about polymers, you could talk about semiconductors. And I thought, how boring would it be to teach in that way? That doesn't seem like very much fun to me, because I'd just be rhyming off rote information. And I've always been more about trying to understand principles, and then you could apply those principles to something else.
So you're really breaking the traditional,
Yes.
In a way, the traditional way of presenting the topic, which is great. So it's a newly innovative, completely fresh way of looking at material sciences.
Well,
material science, I'm sorry, I keep on saying sciences, it should be science.
So I wanted to present it from the point of view of the different physical properties, which is also the way I think. And then you can see common elements in this, like the relationship between electrical properties and magnetic properties. And then my goal was that if a student or anybody who's reading this book then saw some new material, they'd say, oh, now I get it. It has this property because of that, because of its structure. And then they'd have something to hang on to rather than just a bunch of loose facts that this is like this and this is like that. So that was always my goal.
Yeah, well, very well done, Marianne. Congratulations again. So shall we move to the next What are these pictures represent? Like these are your research group, presumably,
yes,
right?
Yes, this is just a few pictures of my research group from recent years where I had good digital images, but my group started when I started as an assistant professor and built up, and I've had wonderful, wonderful people working in my group.
You had the tune of 50 graduate students and postdocs and something like 70 plus undergraduate.
Yes, total, not at any one time. I think the most I ever had was maybe 15 people in the summer when there were a lot of summer students. But yes, a lot of people. It's like a second family, an academic family. I keep in touch with most of them.
And we're going to go to the first family later.
Sure.
but before we leave that point, what is your philosophy in mentoring and training these young aspiring scientists?
Well, my feeling is that they should have some project where they have independent input into the project. Mm-hmm. Now, some people run their research groups differently. They run as teams that are trying to solve a project, and everybody has their piece in the project. I preferred, and I started this from the beginning, and not everybody likes this, but anyhow, I preferred to have students who were pretty much the only one working on that project, and they had to solve one aspect of the project. There might have been a prior graduate student and maybe another one after them.
So they don't overlap too much.
They don't overlap very much at all. And that was kind of on purpose to make them really stand for themselves when they go to defend. That they were, I mean, often their publications were with many people and they fit into a bigger project. But I wanted them to have that independence because that's what being a researcher really is thinking for yourself. And it's not being told, do this, do that, not being technicians and pairs of hands, but really helping them become independent researchers by guiding them towards that.
Nothing wrong with technicians, but it's just a different...
Oh, yeah, it's a different mindset. Yes, when you're working
mindset.
Towards a degree, you have to take ownership of that degree.
And how did you create supportive and innovative, inclusive, egalitarian, equitable type of atmosphere in this lab?
Well, I wouldn't say any lab is like any group of people is always, all peaches and cream. But I think respect is the most important thing. Right. That you don't leave equipment in bad repair when somebody else is going to be using that equipment right after you. And you respect that people come from different aspects. And having people from so many different cultural backgrounds is fantastic for science. This is so important.
Like you had students coming from engineering, chemistry, physics, math.
Yes, and also their home country culture too.
Oh.
Yes, so many international students, many excellent Canadian students too. And I think having all that mix, yet having a common goal of trying to understand thermal properties, and maybe they have their own project, but there are always links between the projects as well. Where somebody could say, oh, yes, but what about this? When we'd had group meetings to somebody who's working on a different aspect. And respect is really the most important thing. And science, there's no harm in saying you made a mistake in science because it may be one step backwards and then two steps forward. But science has to be self-correcting.
I agree 100%. And reflecting on your career, Marianne, how did you, we touched on this a little bit at the beginning of this conversation, but how did you deal with the systematic barriers that were against women, for example, in science, and how did you proceed through that? And what would you say to a young person that is considering STEM if they are, for example, a woman or an underrepresented minority these days?
First off, I think I was lucky because my parents really encouraged me to think and to ask questions. In fact, our household, I was just recently listening to some old tapes of what our household was like when I was a kid, and it was very, very noisy and argumentative because we always wanted to come to the truth. And I think having two older brothers, probably helped me develop a thick skin, rather, early on. And you have to learn to stand for yourself. Mm-hmm. And there have been times when I've felt semi-defeated and just had to regroup and come back another day and do something. But I'll go back to that banner. Why not? If you feel you have a contribution to make to science, oh, come on, give it to us because we need all the smart minds we can have. And not just smart minds. One of my former students reminded me the other day that the most brilliant of students don't always have the most brilliant careers. It's the people who have stamina and who don't give up and who have emotional strength to keep going. they can often be persistence and world smarts and know how to get around things and know how to talk to people to get things done.
And politically savvy in a way.
Yes, yes. Who know, yes, there's no point in going down this aisle, but let's go down this one because this is going to be more fruitful and more people will get behind this. So all of that, the people skills are often underplayed in science. But believe me, if you have no people skills, which I could say probably Einstein didn't have great people skills, but he was working as a singular person then.
But he's the exception of the rule.
Yes, yes. And that's a very rare person who could do that these days and still be a successful scientist.
Right. On a related note, you're widely recognized for science outreach. CBC radio's Maritime Noon Quirks and Quarks. You've done school lectures, even witnessing before the Canadian House of Commons in Ottawa. So what are you trying to achieve with these out of the norm? Most academics don't do this kind of thing. Most academics are in the lab doing their research, but you've done beyond the lab. You've gone beyond the lab and did this. What are you trying to achieve, and how much have you achieved of these goals?
First off, the public pays for our research through research grants through the government. So I think the public deserves to know what we're doing. And I think it's becoming much more fashionable now to make the public aware of what we're doing. And with my students, I always tried to interest them also in joining in these public outreach activities, because to be able to communicate what you've done, well, there's a saying in science, if you haven't communicated it, you haven't actually done it. Because if you just keep it to yourself without writing it or talking about it, then you're not complete in your story.
Yeah.
And also people will challenge you as you are trying to communicate things, and it makes you look at things in a new way. So I always enjoyed talking to people in the general public, trying to make it simple but not incorrect, which is a fine line to walk, but also seeing people spark their interest in what you're doing as well.
And you've even written children's science books, organized National Chemistry Week, wrote more than 70 articles for the general public. So what is driving you to invest in this initiative, and what impact have you achieved?
Now, the two children's booklets that I wrote were part of National Chemistry Week. I was on the Canadian Society for Chemistry Board of Directors, which I understand you've also been on.
Right.
And my portfolio was looking after National Chemistry Week. And I thought, that's great. I'm going to start some booklets for school teachers, for the teachers to be able to do some science with the kids. Because I know that teachers are, some teachers are kind of afraid of science and need a nice entryway into this. And my children were quite young at the time. So those booklets were developed with National Chemistry Week. I found out I had to raise the money, by the way. But we did raise the money to make these booklets. And my children and their classmates and their teachers were all helpful in the work preparing those booklets and testing those booklets on a test group. And they were printed, and tens of thousands of copies were sent around the country. In fact, I had to put together a group of students to stuff those envelopes ourselves. That was also part of the work. I've never been afraid of work. But one of the most amazing things was my daughter is now a teacher, and she was teaching in Vancouver, and I was visiting her class to do some science things with her students. One of her colleagues said, "Look at this. I have this booklet." And I said, "Look, turn to the other side." And she looked at the back, and there was my name in tiny print on the back of this. And she was using it some decades later, and it was all beat up. And that just really warmed my heart.
Oh, great. And given your teaching accolades, because you were rewarded in many ways for your teaching excellence, for example, by Dalhousie University Teaching Excellence Award, the Union Carbide Award, the American Chemical Society Sustainability Award in education, how would you summarize what made you such an excellent teacher?
That's hard to summarize it in any generality, because I think every person has to find their own style as a teacher. And my feeling is that if you're organized, that's part of the battle. Students do not like to see a professor who is disorganized. And I'm sorry to say some are. And that doesn't mean you can't learn from them, but it makes it harder to be learning from them. And I think you have to teach with true interest and passion for what you're teaching. And all of us have had to teach some things. I'm thinking about when I taught first-year chemistry, and there were some aspects that were not my passion. But I had to find something interesting so that I could hook myself first and then the class to join with me in enjoying that topic as much as any of the other topics.
Yeah.
So I guess those are a few of the things that I would say.
I guess there are some of the recognition certificates in one of the images here, right? Here it is.
Well, one was from APICS for science communication. I think that was all part of this. Same thing you're talking about, the American Chemical Society for Incorporation of Sustainability into Chemical Education. That was largely for a graduate course I helped develop on sustainable aspects of materials chemistry. And that course is still being given, and things like life cycle analysis, things that are not normally taught to chemistry and physics students.
What does sustainable exactly mean? Like, I have a vague understanding, but not a precise understanding of what the word means or entails.
Sustainable really means that you're using something, could be earth materials or whatever, but you're also keeping an eye on the future use of those for times to come. So if we consume water to make a product, we should also be thinking that water, we should reduce the amount of use that we possibly could, as much as we possibly could, and we should return that water to the environment in a clean way so that it could be used again, so that the world will be sustained. And you're right that sustainability is used a lot, and it's sometimes a buzzword, sometimes overused, even in terms of what I would call greenwashing, where people say something but it's beyond the truth.
Greenwashing?
Yes. I'm sorry to say, and this is one of the things that I will continue to speak out about when I see things that I feel are overstatements of
sustainability, like
claiming,
over-claiming sustainability.
Yes.
I see.
Yes.
So, Marianne, let's forget all the titles and let's forget all the science. You're a human being and you have a family and you have people that you care for and they care for you. So, how did that shape you, for example? And can you tell us a little bit more about your family?
Sure. Well, I'll start with my husband, Rob, because he's the most important person in my life. And one of the pictures here is us as we were finishing our PhDs in chemistry. We both did our PhDs in chemistry at McMaster University. That's where we met in a lab. He'll be happy to tell you I went in there looking for another guy and I found him. And that's true, but it's a longer story. We defended our PhDs one day apart.
Wow, so, 1 day apart?
1 day apart. I was Monday, he was Tuesday.
Were you married at that time?
Yes, we were married. We married halfway through graduate studies. And he has been the wind beneath my wings for this year will be 48 years we've been married.
Wow,
yep.
Congratulations.
And we've done a lot of things together, and he's always there for me, and he's always my sounding board, and I don't think he's ever said to me, "That's stupid." And very often he said, well, just try it if I have some idea for something.
Now, Professor Robert White is also a chemist in the same department you are. Have you ever collaborated? Have you ever co-written papers, like joint papers, or had a research student jointly? Or we
actually tried to stay separate in our professional careers so that we were not infringing on one another, and we were not going to be bringing any conflicts home. We were never on the same committees, for example. But once, one of his students found something that melted in a very weird way. It melted twice, melted and then melted again, and which is a weird thing to have happen. So we sorted that out and we published a paper together on that.
Wow, so you have only one out of your 200 papers, you have one paper?
Yes,
Do you speak science at home? Do you talk science all the time?
Yeah, if he's strong in organic chemistry, and if I have a stupid question about organic chemistry, which was never my strength, I have no problem asking him and getting straight about it.
What is his main area?
His area right now is looking at stability of ions that come from mass spectrometry.
Okay.
And looking at those as they fall apart in a mass spec and why they fall apart in the way that they do, and how you can use that for analysis.
And Marianne, how about your collaborators? And any thoughts? I mean, without feel free to mention names or not mentioning names so that you don't forget. I don't know, whatever.
Well, I've had wonderful collaborators. First, I have to mention my research group. The students and postdocs who I've worked with have all been collaborators. It's a real partnership in research. It's not. If it's a hierarchy, it's probably not going to work out very well. And
so it's flat.
It's in science, not completely flat.
In North America, we're flat
much
in the groups, right?
Flatter than some other countries.
Than some other countries,
yes. And I've also had tremendous collaborators at Dalhousie University, and often we have things that we think about in similar but slightly different ways.
Was the university supportive of you in general?
Oh, of course, yes. I wouldn't have stayed at the same university for over 40 years if they weren't supportive. Yes, Dalhousie, somebody asked me once, what is the best and worst thing about Dalhousie University? And at the time we were just getting the Institute for Research and Materials started. And it was something that other universities would have said that's impossible to do. But Dalhousie never stood in our way of doing it because it was a grassroots organization from the beginning. And they also maybe didn't help us as much, made us stand on our own 2 feet, raising our own money. So the answer is you could do what you want, but you have to do it yourself. And things have changed because of the structure of research, but I certainly felt that way when I was early in my career and really building things up. But I've had wonderful collaborators at Dalhousie, and I've had collaborators from all around the world, and I'd like to mention one by name, and that's Bojan Marinkovic. He is a professor in Rio de Janeiro at the Catholic University there, and I met him, this is why I'm telling you this story, I met him on a bus in Malta.
Wow.
I was at a conference in Malta, and they had an afternoon off where we were going to see some ancient artifacts, which was very interesting. And on the bus ride, we sat together. We didn't know each other before then. And we got talking, and he was at the very beginning of his career as an academic, and I was mid-stride in my career. And we've worked together. He's an engineer, ceramics engineer. I'm more of a scientist. We worked together and published many papers, including one this year.
Wow.
So over the years, we've published a lot together. We've had our students visit each other's labs for extensive periods of time. He's been here, I've been there. And we really worked together. He's now head of his department, so he's now facing the academic side of things that is the administration and how to handle that in a country that's in quite a bit of turmoil, Brazil. So we've been very close friends and good collaborators for a long time. And I mention this story because you never know what can come from sitting down with a stranger you don't know and talking to them. And science has a very low barrier for getting to know one another. And just after we had met, there was a North American possibility for funding between Canada and countries in the southern hemisphere. South America, I think it was North America, South America collaborations. So we applied for that. That was his first grant.
Oh, wow.
And,
so you got it.
We got it, and then he helped me get another grant through the U.S. And anyhow, we worked very successfully for many, many years together.
This is great.
So you just never know how things will go.
So proceeding with the images here.
Yes, so I have a family. I had 2 children, a boy and a girl. I will mention that I had both of those children when I was an assistant professor in pre-tenure. So my life was pretty full at that time period. I don't know much about what happened in the world during
people
that
don't
time.
appreciate what mothers have to do, and maybe now people are more conscious of this, but probably during
Yes.
earlier times it was considered as a liability almost, to have children.
And very few women
Right?
scientists did have children. There weren't that many women scientists, and very few had children. But if I had to choose between a career in science and being a mother, I would choose being a mother.
Wow.
I think you make a long, long-lasting contribution to the world. And if you're lucky, you can have grandchildren, and I have 3 grandchildren.
Oh, you had? Oh.
Yes, and that is really the jackpot.
So
Completely.
you have a daughter and a son.
Yes,
So
and a granddaughter and 2 grandsons.
And a granddaughter and 2 sons.
Yes. So my grandchildren ask me lots of questions, and I often get those texts, Grandma, I have a question for you about how something or other works, and I'm very happy to engage them in a discussion.
So, Marianne, what's next?
Well, I'm retired officially, but we say in our family retired because my husband and I are both still writing papers and we're still involved in research. We're not working at it as full-time as we once were, which is good because we have other aspects of our life to continue on. But I'm continuing to work in the area, especially of phase change materials. Right. There's so much that needs to be done in this world. We have such big problems. And I mentioned before about privilege and responsibility. I think when you have knowledge, you have a responsibility to share that knowledge. And the work we've been doing and the work we will do yet on phase change materials, I believe can really make a difference in the world. And I like to spend time being a grandma too.
So what is this fun picture then?
Well, I want to remind anybody who's watching this is that you should also have some fun in your life, that you should have some fun And I'll just finish with a tribute to my husband, who one of the best things about him is he totally gets me. And the very best present he ever gave me probably cost him less than $20. And it's this. He knows.
Snowflake inspector.
He knows that I am very adamant that snowflakes, like the Order of Canada pin, must have 6 points. This is how snowflakes form. And in the winter, when I see those 4-pointed or 8-pointed snowflakes in windows, I now have official status to be able to talk to those people and to show them how to make 6-pointed snowflakes.
Wow, that was one fantastic closing for this interview, Marianne. Thank you very much for coming and being with us. And we have a tiny little thing here for you. It's just a tiny little present from Mount St. Vincent University.
Thank you so much,
Oh,
Shirreff. It's a privilege to have a chance.
The privilege is all mine, for sure.
Just have a chance to sit back and look at life.
Thank you very much, Marianne.
Thank you.
Well, thank you very much for the audience, and we'll see you next time on A Conversation with a Scientist. Thank you.